Good afternoon, students. For today's session, we will be seeing the FHSS frequency hopping spectrum, and we will be seeing the CD continuation of the CDMA, one of the multiple axis. So previously, we have seen the concept of the pseudo random, how we are going to generate a pseudo random, and the basis of the spec spectrum. Why we use this spec spectrum? What are the approaches we have in the spec spectrum? And what is the general block diagram, how this spectrum system operate. So here the input signal data is there. You have an encoder, and that encoder will encode your input bit of data, okay, to NRSet or any kind of bits of data, and modulator. You have a modulator here. So we have seen different modulator techniques, and we are going to use a separate pseudo random generator, PN sequence generator. So here you have at the transmitter as well as the receiver module. So this generator will generate a random sequence of bits. It's called as spreading codes. So it is engulfed with the incoming signal from the channel encoder, and it is given to the channel, right? So in the channel, it has been traveled, and some noise will be added or dropping of signal will be there in the channel. Okay, so that signal is received by the demodulator. There is another spreading code that that the same sequence has been generated at the receiver also, and the channel decoder decodes the incoming data and give it to the output. So demodulator use that is the same spreading codes to demodulate the spectrum signal. So same spreading codes are being used for the modulator section and the demodulator section. That ensures that there any hackers or anyone those who are intermediate on the channel can it will feel like difficult to decode the data. So this is a widespread used one of the techniques to send signal in via channel. Okay, so this is we have seen, and we have said about what is the spreading means, and how it relate with the bandwidth, and we have advantage we have seen, and we have seen how this PN sequence been generated randomly, okay, using some 4 shift registers and a modular to editor. So depending upon the number of shift registers, your sequence has been generate number of bits been generated, as well as the period depends upon the 2 power n minus 1. Okay, n is the number of registers. So you have taken n is equal to 4. 2 power 4 minus 1, we will be having 15 number of possible random PN sequences. So in this way, you can able to uh, generate this Sunda random noise. So it's deterministic or periodic. Okay, it's mostly it's deterministic in nature, and it's linear. You have a linear feedback with shift registers. So coming to that properties of the, we have seen the 3 properties. One is balance property, run property, and the autocorrelation property. So it all determines like when you take one of the code, final PN sequence can be taken from the C naught. Okay, so C naught gives the final sequence that is the output sequence PN code. So you can see there is a bit length of PN sequence code. So there you have to take number of ones and number of zeros. So probably what happens is you will get number of ones higher for the less number of PN sequence code. Has a higher number of ones be higher rather than the zero. So if you have a greater number of PN sequence code, then a ones and zeros will be, if you calculate number of ones and zero, it will be equal. So in this way, you can able to set a balance property between the number of ones and zeros. Okay. So P naught P of 1 equal to number of 1 divided by n. Okay, like say P of 0 is equal to number of ones divided by n. N is 2. Okay. So here we will say the run property like n plus 1 by 2. Okay, so n can be taken, capital of n can be taken as 15. So 15 plus 1 by 2, you get as 8. Okay. So it determines the here the number of sequence of ones being generated. You will see how many pairs you have. So once you have like if you take one, you will have nearly, if you converge it, you will have one, two, three, four sets of consecutive ones you can able to see. Okay. And if you see the number of zeros, you have consecutive zeros. So likewise you can able to determine the run from the run properties from the left to right, how many runs similarly you have for a bit period of zeros and one. So third one is autocorrelation property. R of t is equal to 1 by n of summation c of n minus t, d is the delay. So c of n minus 1, let us take delay of 1. Then you have, for that you have to cyclically, okay, cyclically shift this to the left hand side, and this the front the MSB will be taken on the next bit on the cn minus 1. So likewise you can able to shift it, and you can able to okay, you can able to find out the CFN minus 1. So when you multiply both together, minus minus, okay, plus minus plus minus, you get 1 into 1 is 1. So similarly CFN and CFN minus 1 you will be getting. So this is the thing you'll be getting here, and if you calculate the 1 by 15, and if you just add together, okay, the sequence, sum it together, and you get r of 0 is 15, cancel it out 1. Okay. So like you similarly r of 1 and r of 2, you get 1, okay, with respect to n and r. So we get a sequence of like this. Okay. So the maximum you have 1, and the negative, okay, and the negative you have minus 1 by 15. Okay, because we have some minus value here. Two minus values you have. So you will get a distribution of like this. So in this way you can able to find out the autocorrelation property, find out how the bits have been correlated together with respect to a delay sequence. So next one is the array sequence space spectrum. Here we have seen the it's one of the way of spreading the code. It is pseudo noise where chip rate, okay, chip rate can be taken as RC, okay, RC, and small chip duration, the bit duration can be taken as TB, okay, and chip duration can be taken as TC. So this can be taken as 1 bit duration, which is okay, and the chip and the whole chip duration can be taken as the this one, okay, TD. So in sorry, bit duration can be taken as GD, and TB, okay, bit duration from this point, and the chip duration can be taken as the number of chips being allocated. Okay, so from the P of T can able chip durations, one chip. So likewise, chip rate, we have to calculate the a number of chip rate R of C. So here the processing gain is taken as the ratio of TB by TC is equal to N. So when you calculate the chip bit duration, okay, is a ratio of bit duration and the chip duration, R by RC by RB. That is between after spreading and between after before spreading. So after C of t is equal to M of t into P of t plus I of t. Okay. So there is a I of t pin sequence interference been added with the channel. Okay. So this interference can be of any kind of ISA signal or any kind of co-channel interference. So this has been added together with the coded signal. So in this way you can able to get a modulated, okay, modulated message, okay, from the input, which should be exactly similar to the. So here also they use the same p encode sequence generator, and local oscillator is being given, that is cos so omega t, okay, and there is a jammer or interference being added. So you can say the sequence, you can see that the DC will be higher and the N will be greater, such a way that the SNR should be as high as possible to minimize the noise. So at last you will get the M of t, P of t plus I of t as the intermediate message signal, but our main parameter is M cap of t. So that's our information which has to be retrieved. So The same sequence generator will PN sequence generator will be calculated here. This will be taken off P of t, and the I of t will be taken off. So interference will be taken off. So we'll get retrieve only the m cap of t. So this m cap of t and m of t, that is the input message, should be equal together. So in this way, by you can use by using some pseudo random sequence generator, and by using some interference or jammer, you can able to calculate the that is equal to send the signal from the sender to the receiver with the less number of bit drop and errors. So it's mainly used for long distance communication or satellite communication, because there you have a prone to environment such a way that any bit signal may get lost to attenuation, scattering. You have a lot of phenomena there. Okay, so in this way, information has to be retrieved back correctly. Okay, such a way the retransmission protocol is there. Retransmission protocol will ensure that the last bits will be retransmitted back, and make sure the internet recipient receive the full data bit. So here coming on to the frequency hopping spectrum, um, here the we will see limitations of DSS. So here what happens is the use of BPSK modulation. So here its use of BPSK modulation. So there is no need of non-coherent detection schemes in the DSS. So that's one limit where you're going to add an extra interference block over there to take away the interference signal. And next one is SNR is high, and the N is high, noise is high, and the chip rate is quite high. So this SNR is high is quite good, but the noise is greater. That has to be limited as possible. But the chip duration should be as much small as possible compared to the DSS. So the spectrum is utilized greater, where there is a chance of like fall off may happen, where you can say you won't receive exactly the square waveform for the bit duration. There is a chance like exactly like this you will be getting. So there is a steep rise and steep fall here at this pulse. So this will affect the response time. So we can say that in a bit duration TB, there are some n number of sequence. Okay, if 2 is added, a lot of sequence will be added. Okay, so TC1 is greater than TC2. So there it limits that whenever you have a small bit very very small. Okay, what happens is like your required modality will be very much like this. So the transition time will be very much smaller, which will rise to noise. So the transition between the one of the pulse, okay, to the next pulse, okay, is very fast. So this is not practically applicable in a high speed data transmission. So make sure this is one of the limitation in DSS. So that can be overcome by FHSS, frequency hop spectrum hops. Okay, or change. This hopping defines that change in a random manner based pseudo random code. So nothing but the frequency will be changed in a random manner, okay, based on the given PN sequence code. Okay, so you are going to change randomly the frequency and to the in respective with the PN sequence code. So next one is the interference is reduced in the FHSS. So you have some gap, okay, between the sequence. So it makes sure no two frequencies get overlapped each other. And third one is MRA phase modulation scheme is used for this FHSS. So previously all DSSS, okay, CDMA, they use BPSK modulation. So here we use the MRA FSK modulation. So M is the number of elements, so it based on 10 or 12 or 15, depending upon the modulation, number of shift register being used. And the 4 array, if you take 4 array FSK, So let us take 00011011. So here 00 can be taken as frequency 1, 1101 as 2, frequency 2 is 10 as F3 and 11 as F4. Similarly, if you are going to find for 8 array, so 8 array means you have to take 3, okay, 3 bits. So 2 power 3, okay. Uh, so you have to take 3 bit ranges 000 001, so up to like 8 you will have. So you can segregate each every bit code can be taken as the F1, F2, F3 up to Fn up to F8 will be getting. In this way, you can able to split the uh, that is the MRFSK in each and individual frequencies. The generation of FHSS. Here the same as the DSSS. Okay, so here you have a local MRFSK modulation. So there's local oscillator, and here it's multiplied by a frequency synthesizer. Okay, synthesizer and PN code generator, and it's been given to the another modulator here, and one of the signal given to the BPSK, sorry, BPF bandpass filter, and it's been forwarded to the channel. So there's a filtering, that is a synthesizer being added corresponding to the previous DHSS. So likewise, you have the demodulator section. At the demodulation section, you have the same synthesizer and PN code. It has been bandpass filtered, demodulated, and the message signal been retrieved. So estimated message signal can be taken as m cap of t. So here, what happens like the frequency is synthesized, okay, with respect to different frequency slots, with respect to the PN code, okay. So each F1, F2, F3, the signal from the MRA is given slotted out for different frequency slots. So it seems like it has been transmitted to it's been bandpass filter, and it's been okay. Where you have combination of FC and FP. Okay, FC is from the message signal from this channel, plus FP is from the pseudo random noise. So both been added together, given to the channel. Okay, it has been given. It has been delivered. So here the BPSK at the demodulator, it retrieved back at the demodulation side, and the message has been retrieved. Let us see the working principle. Okay, so here let us take F1 y-axis as F1 to F8, x-axis as the bit duration. Okay, TB. Let us take the PN codes for each bit duration 000 001. So 000, it's been slotted out. Okay, and it has been slotted out and it taken as one slot segment. Okay, up to 8 you can take. Okay, for first of the sequence like F1000. Okay, so find out where is 000. It lies on F1. F1, you have to mark it out. And let us take 001 F2, and 001 is lies here, it is F2. Okay, so such a way you can able to hash it down the required the frequency. That's why no two frequency get interfered. That's the main concept in the spectrum. So the frequency get hopped. Okay, one frequency here, another is been hopped to the F3, another been hopped. The change, this is a change been happening. Okay, since there is a change, it is very difficult for the hackers or anyone to retrieve the data. They doesn't know the sequence of this. Okay, so it's very difficult. So it will be in a random fashion. So there are two types of frequency hopping. One is slow frequency hopping and fast frequency hopping. Here let us take RS, the time period is equal to R enough, small enough, or S where it is take the simple duration. Okay, with respect to the center and receiver, it can be written as enough TS. TS can be taken as the simple duration. Okay, and TC is the chip period. So from this small formulation, we'll just find out what this graph determines. Multiple symbols are transmitted on same hop. So if you take like 000 or 1, So if you take any two bit duration symbols, okay, you take a chip, this can be taken as chip period. Both can be combined and be transmitted, okay, in a corresponding frequency. Or else in fast spectrum hopping, it differs by the shift period. Okay, there is n of TC. So what happens here is each and every slip is slotted into two. Okay, so what happens is the duration is quite been reduced, and the frequency hopping will be somewhat fast. So you'll get like fast hopping in this kind of space spectrum. So in a very high-speed telecommunications systems, fast hopping is more being used, whereas you can able to use the slow hopping in a very where system where within which doesn't which doesn't have a high efficiency, doesn't don't want to have a high efficiency output. You can able to go for the slow frequency hopping spectrum transmission. So these are the two types in FHSS. So previously DSSS we have seen. Next one we have seen the FHSS. So here the most predominant way is your interference is very much reduced. Okay, there's no chance of interference, and this one is widely used in the uh, 3G communication systems. So it involves the periodic change of transmission frequency or wideband. Okay, so what's a hop set? The computing to mask set a possible time varying solar random carrier sequence. We take next hop sets. So it's just a small demo of what you have seen. So information signal is there, spreading is being done, pre and spreading is done, and the FHS signal being given in different frequency slots. Okay, de-spreading is done, and decoded information is being done. So this information will be similar, should be similar. So this can be taken as the signal level versus frequency. Okay, you can just plot it down using S1 is different users. Okay, hopping sequence can be taken with respect to users, and the hopping sequence you can see this is what you have drawn there. Okay, so this is a basic hopping process. This is respect to frequency versus time. In time domain, how it resembles like that? It resembles in a fashion of like this. Okay, for a specific bit time period, hoppings will happen. Okay, so different hopping sequence will be done with respect to the time period. This is based on time domain. Previously, you have seen in terms of frequency domain. Block diagram of FHSS modulator. This is the basic block diagram. You can just look at it. We have already seen this on the previous slides. So we use MRI FSK for the modulation and demodulation process. You use a frequency synthesizer and P input generator. It allocate it's been mixed out with the FHS signal with the C of T. Okay, so it's been given to the bandpass filtered and demodulated, and output is being given. So here the signal to interference ratio is one a scenario heard, but there is a term called interference signal to interference ratio related to this formula. So B is a bandwidth, M is the number of users in the FHS system, A is the number of octal codes being used, okay, with this capital, and RP is the signaling rate, bits per second. So the rate should be quite greater than 1, so L should be also should be greater than 1. So this all comes from the coding sequence. You get this RB and L. M from the number of users being allocated for the FHS system. B is the bandwidth. So this will define the signal to interference ratio. It should be a positive value. So some advantage and disadvantage, like FHSs have some high tolerance for narrowband interference. Relative interference avoided. Large frequency hopping bandwidth can be established. More interference tolerance is being achieved. The probability of detection will be much slower compared here. The non-core detection is being not being used here. So that's one of the advantage and disadvantage. So you have seen some this diagram. We have channel 1, channel 2. Okay, a lot of channels is there. We are dividing with respect to time versus the channel. Okay, or transmit or frequency, or this can be taken as the frequency in gigahertz. So f1, f2, f3, f4 up to fn up to gigahertz been plotted out, and it is been time scaled with respect to millisecond. Okay, each and every channel is given in time scaled. So in this way you can able to allocate a channel, okay, with a different frequency. So this is an example of co-located frequency hopping system. So collision avoidance and frequency hopping. So here, collision at the same frequency time slot is not a problem with a single user, but if you take a multiple user, collision can be a problem. Some two of the user attempt to say, use the same frequency time slot. If two users try to use the same frequency, there's a chance of collision. This can be avoided by the calculating the correctly the proper selection of PN's code assigned to each multiple. So the PN code has to be random and randomized such a way that no same code has been generated to different users where they try to collide. Okay, so its the PN sequence has to be generated carefully. Frequency hopping spectrum. There's a you can see the synthesizer, just a base of it is broadcast over multiple frequency in a pseudo random pattern. Okay, so it broadcasts over the multiple frequencies in a pseudo random pattern. Both transmitter and receiver should know the pseudo random pattern to successfully receive. So here the transmitter and receiver should know. If they does not know the pattern sequence, so ultimately this process is being wasted out. So they should know the what kind of random sequence they will be sharing among themselves the same sequence codes between the transmitter and the receiver. So here the FSK modulator, uh, a transmitter and receiver section is being uh, taken as a block diagram. Okay, so we just make a look over it. So it doesn't need a coherent detection. So here, so it doesn't need some extra blocks to detect. Okay, it automatically based on synthesizer and random noise, you can able to make it out. So yeah, the problem is like channel get interfered, like it's in collision can happen. That should be avoided based on the proper PN sequence generator. So frequency hopping in a Bluetooth. Bluetooth, they have a got bands been front and at the back, where intermediate you have a hopped channels. Okay. So Bluetooth is a wireless channel exchanging data over short distance. So we use the Bluetooth, right, for exchanging data over short distance. So they use ISM band 2.45 gigahertz. ISM stands for Industrial Scientific Medicine. So it is a packet-based protocol. It uses some small packets data. Okay, so it's been allocated a PN sequence. Okay, it uses a concept of FHSS. It uses time switching for some channels. Okay, hopping rate is around 1600 times per second. Okay, so per second you have 1600 hoppings being done, up to like up to 8 channels they can able to hop it. So it should be as fast as possible because you're going to receive the data via Bluetooth. So in a nanosecond or you must lesser, you must switch it very fastly these channels. Okay, so that there is no delay happening in the transmission. So frequency hopping and direct space spectrum, the merit sentiments have projected can withstand jamming for the FHS, but similar to, it quite difficult in jamming process. So it's less affect near for problem. So at the far problem is it defines like in nearer to the vicinity, you, you may get the cross interference, but the far you get some delay experience in the signal. So this is called near fault problem. So this is there in DSS as well as in HFSS, but it is less affected in the FHSS. So let's affected by multi-axis interference. So here, since the channel has been segregated frequency, multiple frequency, there's less affected. There's less access for the interference. And the merit is say like it's simpler to implement DSS. Low probability of interception can instead multiple access interference. So demerits frequency acquisition may be difficult. So allocation of faculty may find difficult. Need a forward FEC scheme to combat noise. So there may be a noise in occur. So for that you need to add a FEC, that is forward error correction scheme. Okay, so to retrieve back the original data. So data sequence code acquisition may be difficult, affected by jamming and susceptible to near fault. So his main problem is jamming and near fault problem. So this can be overcome by the FHSS. Salient features of this spectrum like high processing gain, immunity to jamming, greater security, low probability of interception, increased tolerance to multipath, and low interference, easy encryption, multiple access, increased tolerance ratio, increased ranging capacity, that is near and far. So it provides a good security and jamming, immunity to jamming, and high processing gain. So you should make sure the gain is somewhat high while transmission. If you're going to transmit one Bluetooth data to your laptop to your mobile using via Bluetooth, so the gain has to be maintained high. So if there is a deprivation gain, the signal will be lower. Your transmission, that is your reception time, will be higher. He says like when your gain is higher, your transmission may happen in a very faster way, but when the gain is somewhat lower. Okay, so what happens is like it tries to receive small chunks of packets, very long time. So it takes some time to receive the data from the transmitter. So gain has to be high. If gain has to be high means the noise has to be low. If noise is higher, it will overlap with the gain, and the overall gain, total gain will be reduced. And this greater security, okay, since you have this random sequence code, so you have greater security. So this is the main importance of going to the fourth generation mobile phone and fifth generation mobile phone. They use the selling features of the spectrum, okay, for our wireless communication. So code division multiple access. So here, let us take a channel. Okay, so using FHSS, yes, you'll see the CDMA. So here you have a sequence of code. It's a channel, and you have four users. And the four users, you are getting input of D1, D2, D3, D4. That input has been coded with that is like added with multiplied with the random code, that is C1. Okay, that is code sequence, the PN sequence, that is D2 C2, D3 C3, D4 C4. So it ultimately is added in the channel, that is summed together. So this is what this block determines. Such a channel, there are four users. Each user gives their own data that has been multiplied with EPN code and been added in this channel. So they use the orthogonal codes to transmit different signals over same channel. So it uses some codes, okay, to transmit different signals over same channel. So same channel, one channel can able to allocate different users by allocating a different codes for it. Okay, there previously frequency been allocated, here code is been allocated. Okay, random codes. So we'll see that codes. This is in the third generation mobile communication system, the CDMA 2000 wide CDMA, okay, and the HSCP, these are all the high speed networks. So let us take C1, C2, C3, C4 or orthogonal codes. Okay, orthogonal means they multiply both codes be equal to 0. So let us take C1, C2, C3, C4 as these are set of ones and minus 1. Okay, so when you multiply both together, you get, okay. But see, when you multiply the same codes, C3 and C3, you get 4. So you cannot do that. Okay, what only expressive when two different codes are multiplied, you get 0. So likewise, the alternative function is been satisfied. So okay, let us take 1, 2, 3, 4. One has been assigned A1, A2, A3, A4. That can be further assigned as A, okay, A minus A. Let us take like 1. Okay, this A, so it's minus A is 0. Okay, and this is 1 and this is 1. Let us take this one, and this 1011 can be taken as D1, D2, D3, D4. Okay, for example, let us take 1 is A, 0 is minus A. If no data transmit, it is 0. Okay, so if you take D, that is the first user, if it doesn't transmit, it is 0. Okay, if it transmits either like positive, it is 1, negative of A is 0. It is considered like this. So in the channel, let us take it's a multiplication of D1 C1 plus D2. Let us use this formula here. So D1 is A into C1. C1 is 1111. Okay, so multiply it, and similarly you frame this. Okay, so like you see, get C of x is equal to A, that is 1, A into 1, A into 1, plus minus plus. Okay, so just multiply inside. This one is a channel code. It's an integer channel code added. So here Rx, the receiver, okay, with respect to 2. Okay, it take at the receiver side at the 2. Let us take C of x into C2. Okay, that's a channel. You're going to receive it. So we're going to infer that the data transmitted at the D2 is same. So we want to see that the transmitter and receiver should be have a same bit. Okay, so let us see that. So C of x, take the same bit which is you have arrived, write it here. Okay, and you multiply by the C2. C2 is 1 minus 1, 1 1. Okay, so here when you multiply with the C2, okay, this is C2. So once you like to cross multiply with ones, okay, 1 A into 1 A into minus 1 A into, okay, third one 1 and A into minus 1. Likewise you have to then add, then you multiply minus A into 1 A into minus 1. Likewise you get a big sequence, right? So the minus symptoms will cancelled out and you get minus 4A. Fine, minus 4A. So here, when you divide by the normalized, when you normalize it, okay, normalize it, divide by the sequence which you got. Okay, so let us take 4. Let us normalize it 4. 4. This will be the 4 and 4 will be taken off. Because this doesn't want this value 4. It doesn't want to have. Let us normalize. So you'll get minus A. Yeah, minus A. Fine. So what is D2? Since we have taken the second user, right? See the second user, you have D2 as the input. What is D2? D2 is, see here, D2 is minus A. What you received here is minus A. Can you understand? So the received sequence minus A and the transmitted D2, okay, which is nothing but the, from here we consider this minus A. So these and receipt data are same. So in this way, by adding a sequence of orthogonal codes, okay, uh, you can able to send the channel and receive the exact data which is being transmitted by the intended uh, transmitter. If you want to take Rx of 3, so you can use the same CFX and C3. You can have to verify that it will be around A. Okay, Rx of 3 will be A. So this is the CDMA. CDMA, like it number of users occupy the same bandwidth of all the time. That's the main key point. The signals are encoded so the information from an integer transmitter can be detected and recovered only by the property. So here they use the, okay, uh, all users can share the same channel and bandwidth at all time. That's the main thing, at all of the time. Okay, there is a restriction in time on the previous FDMA and DSSS. So here the every number of users can use the same channel at any time. That's what our technology 4G been used, this WCDMA, and this is the base thing. It's been enhanced version. So in 4G they use OFDM, which is an enhanced version of CDMA. OFDM. Okay. So that's why each and every users can able to call at any time and receive at any time. Okay, so they use this kind of techniques. So each receiver section has its own code called address. Okay, and transmission station simply modulate a transmission with the address of the intended receiver whenever it wishes to send a message to the receiver. So you're dealing with the base station and the mobile which you're holding. Okay, so it's kind of address sharing and allocation. It will be done by the CDMA. That's what is here. Hi, okay, going to hi and go, and someone is giving go. It has to go to the intended recipient. It uses separate code. Uses are separate by codes. Different codes being used to separate it. Okay, not inter. If you interfere both this hi and go, so the internet receive this internet it receive hi and go. Okay, there should be a separation. So it is a full replace one two like transceiver. Okay, either way you can able to communicate by two-way. Eliminate the need to engineer reuse the pattern, increase capacity by 6 times, multiple recession increase quality clarity, security and interference reduction is more. That is like you have good security and interference will be less. And this is kind of one of the receiver which has been used in base station terminal rig receiver. We are not going to see that, but they use the PL sequence and the receive sequence. You can see a different delay been used, phase been adjusted, okay, summated and given to this. This is the one thing that they use is base stations, okay, mobiles and the base station rig receiver. And power control like avoids near far effect and increase the mobile unit battery lifetime. Okay, so here has been given, especially the at a near or further in this mobile hot. Forward link power control BTS independently adjusts the power based on the information received from the base station terminal. Independently adjusts the power. So whenever there is a user nearer, it gives less power. So whenever user is more far away, so more power has to be given. So that the power spectrum is being utilized effectively. Reverse link power control, open loop, closed loop. Is due to the transmission of mobile. It monitors the total power received by the main station. Okay. It also closed means it provides the continuous feedback to each mobile so that the mobile varies its power accordingly. So this there is a power allocation scheme. Okay, being done between the BTS and the mobile. Uh, so it's all done inside the mobile signaling board, open loop and the closed loop. So this is a general block diagram of CDNA. We already see that. It has given PSK RF modulator. Here the carrier is being given local oscillator, IF carrier, code generator, PNC code generator. So it's been transmitted to satellite. So from satellite it's been given demodulated code acquisition tracking. Tomorrow we'll see this topic acquisition and tracking. And the correlator will be the balanced modulator we are using. That is a phase selector, bandpass filter. Last the data has been given out. This is one application with respect to satellite communication. So the transmitter use PSK modulator and receiver use the balance modulator. So here the main thing is mobile base station, mobile switching center, authentication center, operation administrative maintenance. These are related to this mobile and base station linkage. So this one is given here. So similar how this mobile is linked to the base station and is servicing, okay, station and the different telephonic system, PST and public switching telephone system. So these are just to look it's not your it's part of your syllabus, but just to make a highlight of what the CDMA in-depth forward channel link, that is like base station to mobile phone. What is this giving traffic control paging sequence syncing pilot. These are signals to be given from here to base station to mobile to base station traffic channel and access channels will be given. So four stage of modes in CDMA like initialization, idle, access, traffic mode. So I think these are related to some examples like in GPS, Bluetooth. Some limitation is like near fault effect will be there, jamming will be there, and availability of contiguous bandwidth, synchronization requirements. Some synchronization has to be done. Some near fault effect will be there, self jamming due to some lot of different ports, these two different ports can be jammed together and crosstalk can happen. Okay, but these are some of the limitations. And you see this different separation between FDMA, differentiating TDMA and CDMA, the whole thing with respect to the parameter. Okay, this can be asked for some 6 to 7 marks. This is a good PPT. Can refer it up. Okay, thank you. Tomorrow we will have